Good morning. My topic name is application of XRD in rechargeable batteries. So let's see the introduction of batteries. Batteries are the energy storage devices that convert chemical energy into the electrical energy. Here is the diagram of lithium-ion battery. Generally, lithium-ion battery is made up of anode, cathode, electrolyte, and the separator. Anode is made up of graphite, cathode is made up of lithium metal oxide, electrolyte is made up of lithium salt, and the separator is made up of the polyethylene and polypropylene. The lithium-ion batteries are a widely used type of rechargeable battery, powering the devices from mobile electronics to the electrical vehicle and the grid storages. The importance of lithium-ion batteries. It has the high energy density and the long cycle life. It is crucial for the modern applications requiring lightweight and compact energy storages. It has some environmental benefits such as the lower emission in electrical mobility and the renewable energy storages. Let's see the working principle of lithium-ion batteries. At the time of charging, we connect the charger between the electrolytes. Generally, the lithium are present at cathode in the form of lithium metal oxide. When current I flow from the charger to the cathode, the lithium reduces to the lithium plus ions, and it travels to the electrolyte toward the anode and react with the carbon to form the lithiated carbon. Here, at cathode, the lithium metal oxide reduces to lithium plus ion and metal oxide, and at anode, the carbon reacts with lithium ion to form the lithiated carbon. The overall cell reaction is lithium metal oxide plus carbon gives metal oxide plus lithiated carbon. At discharging, we connect the load between the electrodes. In this state, the lithium is present in the form of lithiated carbon at the anode. When the current I flows from the load to the anodes, the lithiated carbon reduces to lithium plus ions. Then this lithium plus ions travels to the electrolyte and react with the metal oxide at cathode and form the lithium metal oxide. Here, at cathode, the metal oxide react with lithium ion to form the lithium metal oxide, and at anode, lithiated carbon reduces to lithium ion plus carbon. The overall cell reaction is the metal oxide plus lithiated carbon gives lithium metal oxide plus carbon. Let's see the application of XRD for battery materials. Battery materials can be analyzed in static mode as well as in operand mode. For cathode material, XRD can be used for the qualitative analysis as well as quantitative analysis. It is also used for finding the lattice parameters to analyze crystal structure and the crystal size. In separators, XRD is used for the orientation analysis and the crystallinity analysis. And for solid electrolytes, the XRD is used for the qualitative analysis as well as quantitative analysis and for the crystal structure determination. And for anode materials, it is used for the qualitative analysis and for the lattice parameter identifications. In operando mode, XRD is used for the structural analysis and the evaluation of degradation during charging and the discharging. So let's see the first application, that is the phase identification. This is the general XRD diffractogram, which contains the information of diffraction angle 2 theta on its x-axis and the information of intensity on a y-axis. The peak width contains the information about the crystalline size of a material, and the horizontal peaks contain the information about the crystal structure, lattice parameters, and in polymer the long period structures. The intensity of a peak contains the information about the crystal structure, quantification, and the percentage of crystallinity. So, first step is to analyze XRD data and identifying the peaks. This is known as the peak search. Then we have to perform the profile fitting, where the blue curve represents the calculated profile and the red curve represents the raw data. Then we have to compare the data with the standard database. Generally, uh, the software can compare our data with the standard database and gives the information about the phase and the phase and give information about the phase. So once peak identified, the two theta position and intensities are compared against an XRD database. High quality database may contain over 1,000,000 entries, and the software can match your reflectogram to identify the correct phase. For example, the software detected this is the lithium cobalt nickel manganese oxide. So the another application is the chemical composition by XRD. We can find the chemical composition using the XRD if the material is crystalline. Suppose let's consider the lithium cobalt oxide. Here are the three databases of lithium cobalt oxide having different lithium concentration. The first data is for 100% lithium, second for the 75% lithium, and third is for the 27% lithium. As the percentage of lithium changes, the two theta values, that is peak, are shifted. Peak also changes. Let's see. Suppose for 100% in lithium cobalt oxide, for 100% lithium, there is the 1 2 theta position, and for 75% and 27% there are the another positions. This the shift in the peaks is correspond to the percentage of lithium content. The peak angle 2 theta changes based on the lithium concentration because the lattice parameter changes with the composition. By analyzing these peak shifts, we can estimate the elements percentages based on the 2 theta shift information, which reflect the lattice parameter variations. Here are the steps for finding the chemical composition by XRD. First of all, we have to obtain the XRD patterns of our known composition. Then we have to identify the peak position. Then we have to create a calibration curve. Then we have to measure the unknown sample, and using the calibration curve we have to estimate the composition of unknown sample based on the observed peak shift. Suppose here is the some given data, that is lithium occupancy in percentage and the peak position, that is 2 theta values. If we measure an unknown sample and find the peak position at 2 theta equal to 21.5 degree, we can use the calibration curve to estimate the lithium occupancy. In this case, the lithium occupancy will be roughly between 75% and 27%, cause the peak position is 21.5. So the another application is the rate weight analysis. The rate weight refinement is the method for fitting a calculated diffraction pattern to the raw XRD data to extract the detailed structure information. We take this data, and after peak search we found this is the lithium cobalt manganese oxide by phase identification. In rate weight refinement, we use the software which calculate the diffraction pattern based on the crystal structure and found by the phase identification. The blue curve represents the calculated profile, while the red curve is the raw data. The goal is to fit the calculated profile to the raw data as accurately as possible. Through this analysis, we can obtain the detailed parameters like crystal structure, atomic coordinates, and the occupancy factors. The another application is the percentage of crystallinity. Generally, the polymers often contain both crystalline and the amorphous regions, which affect the diffraction pattern. Using XRD, we can find the percentage of crystallinity. This is the XRD pattern of one of the polymer. The sharp peaks from this data are due to the crystalline phase, and the hollow peak is due to the amorphous. By integrating the intensity of sharp peak versus the broad hollow peak, we can estimate the relative weight fraction of crystalline versus the amorphous phase. Similarly, we can find the percentage of crystallinity using this formula. That is, the percentage of crystalline content equal to the area of crystalline peak upon total area into 100. Let's see one example. If the area of crystalline peak is 500 and the area of amorphous hump is 500, then the total area become 1000, and the percentage of crystalline content equal to 500 upon 1000 into 100, which is equal to 15%. So the sample has roughly 50% crystalline content. Our another application is crystalline size and distribution. The XRD also enables the analysis of crystallite size and the size distribution. First, we have to peak search and profile fitting. Then we have to phase identification by comparing this with a database. After identifying the phase, we can refine the structure to calculate the crystalline size distribution. The software provides us a volume-based and number-based distribution profile, where the x-axis contains the information about crystalline size and y-axis having the information about distribution. From this graph, the average particle size is equal to 200, is approximately equal to 200 angstroms. So, how to calculate the crystalline size? Using the Scherer equation, we can calculate the crystalline size. The Scherer equation is D equal to K lambda upon beta cos theta, where D is the crystalline size, K is the shape factor, usually 0.94, and lambda is the X-ray wavelength. The beta is the full width half maxima and in radians, and theta is the Bragg's angle. So let's see how to determine the full width and the half maximum. In first example, the total intensity of peak is considered as the maxima, that is F max, and half of F max is between x1 and x2. So the width at half maxima, that is from x1 to x2, is considered as the full width half maxima. If our XRD data not starts from 0, it has some background noise, then we have to measure the maxima from the baseline of this curve. So here the Imax is here, half of the Imax is here, and the full width half maxima is the distance between this to this. So let's see one example. Suppose we have the XRD pattern with a peak to theta equal to 31.8 degree and a full width half maxima of 0.5 degree. Using the Scherer equation, we can find the crystalline size. For this, first we have to convert the full width half maxima in radians, which is beta equal to 0.5 degree into pi by 180 equal to 0.0087 radian. By Debye-Scherer formula, D equal to K lambda upon beta cos theta, we can find the crystalline size. By putting these values and calculating, we get the crystalline size. The another application is the intercalation mechanism of battery using the in situ XRD. Here, in the XRD pattern of 2 theta of 1.6 to 1.9 degree, showing the shifting and the splitting of graphite 002 peak with the change of x values in LIX C6. The XRD pattern observations are at the starting from x equal to 0 to 0.08. There is an asymmetrical 002 peak with minor displacing changes from 0.36 angstrom to 3.39 angstrom. This attributes to random lithium intercalation. As x increases from 0.08 to 0.3, the displacing of the 002 peak increases to 3.49 angstrom, and the peak symmetry improves due to order lithium distribution caused by the repulsive interactions. From 0.3 to 0.5, the minimal changes in displacing and the peak intensities occur as lithium destabilizes the graphite's heavy structure, pushing it toward a AA lattice configuration. So now the formation of lithium rich phase. Uh, Beyond the x equal to 0.5, peak weakens and eventually vanishes, while a new peak at 2 theta equal to 1.69 appears, indicating the formation of lithium rich phase. A concentration gradient of lithium develops within the graphite, leading to intermediate phases that signal the gradual transition from lithium poor to lithium rich states as lithium diffuses from the surface inward. This is the only in situ XRDs of charging phase. So the another application is to calculation of a battery life using a in situ XRD. For calculating the battery life using in situ XRD, we have to first calculate the degradation constant K. For this, we have to extract the cycle number and the peak intensity data from the XRD. Then we have to plot the peak intensity C versus the cycle number T. Then we have to use the exponential decay model. The degradation of the battery capacity, that is intensity, can be modeled using the exponential decay model, which is C of t equal to C naught into e raised to minus kt, where C of t is the capacity at the cycle t, C naught is the initial capacity, which is generally 100%, k is the degradation rate constant, and t is the cycle number. Using software tool, we have to fit the exponential decay model to data, and we have to find k. The fitted parameter will give us the initial capacity C naught and the degradation rate constant K. The degradation rate constant K indicates how quickly the battery capacity degrades over time. A lower the K values means lower degradation and a longer battery life. The peak intensity often corresponds to a battery capacity. Consider a lithium-ion battery with a cathode material. Suppose you measure the XRD pattern and the capacity at various cycles. Suppose here is the cycle number from 0, 50, 100, 150 and 200. As cycle number increases, the peak intensity percentage decreases from 100 to 80. At the same time, the capacity percentage decreases from 100 to 80 degree. That is, by these results, the peak intensity and the battery capacity are similar, are generally similar. So our next step for battery life calculation using the degradation rate constant is to determine for the calculation of battery life using degradation rate constant K. First we have to determine the degradation rate constant K. Then we have to set the initial capacity C naught. Generally the initial capacity is 100% for new batteries, and we have to define the capacity threshold. The capacity threshold is the percentage below which the battery are considered as the dead, and the use of exponential decay model, which is the C of t equal to C naught into e raised to minus kt. By rearranging this equation, we will get the battery life time t. By rearranging this equation, we will get C of t upon C naught equal to e raised to minus kt. By taking logarithm on both sides, we will get log C of t upon C naught equal to minus kt. And by dividing minus k on both sides, we get t equal to log Ct upon C naught upon minus k. This equation t equal to log C of t upon C naught divided by minus k gives the battery life for us. Let's see one example. Suppose the initial capacity C naught is 100 units in mAh. The degradation rate constant is 0.001 per cycle, and the capacity threshold is 80% of the initial capacity, which is 80 units. Using this formula, we get t equal to log 80 upon 100 divided by minus 0.001. By calculating, we get the t is approximately equal to 223 cycles, that is 223 cycles. That's how we can find the battery life using the XRD. Thank you.